So, hello and welcome to the Reinforcer webinar entitled Discovering the Unexplored Deep Marine Environment with the KM3-NET Neutrino Telescope. So the KM3-NET telescope, that stands for Kilometer Cube Neutrino Telescope, and it's a really very unique telescope which is deployed at the bottom of the sea. And unlike other telescopes, it doesn't look up to the sky, but it actually looks down through the Earth at the sky on the other side of the Earth. So it's located very deep in the sea, completely in the dark. And with it, we not only detect neutrinos, but we can also explore the deep marine environment. So in this webinar, we want to engage our citizen scientists to help us make use of this very special telescope to understand better the marine environment, and that will help us to detect these neutrinos. So let me see if I can. So this is the plan of the webinar today. So I'll start with a kind of this welcome and an introduction into all the projects that are involved inside the Reinforced Citizen Science program. Then Gwenhael will introduce what are the neutrinos I've just been talking about and how KM3-NET works and can detect neutrinos. Gwenhael will explain that we can also we can see light, and with that light we can study bioluminescence. So Severine is an expert in studies of bioluminescent organisms in the deep sea. So she will explain to us how all that works and how animals can make light in the sea and what we can learn from seeing the light patterns they make. The neutrino telescope not only has eyes, but it also has ears, and with it we listen to all the acoustic sounds around the telescope. So that can immediately opens to us a kind of world of bioacoustics, and we can listen to the whales and the dolphins. And Hervé Glotin is an expert in these bioacoustic studies, not only with KM3-NET, but with many other experiments, mainly based in the Mediterranean Sea. So he'll tell us about that. Then Remy will be the last of our speakers, and he'll talk about the tools that we're developing to help our citizen scientists to study these optical and acoustic backgrounds. And then at the end, we'll have a question and answer session and hopefully summarize what we've learned and your impressions and how you can engage in the project. So each talk is about 10 minutes, so we won't take too much of your time, only about an hour, I hope. We hope there will be questions, and if you're lucky, you might even get some answers. But that will be done through the Q&A panel, which you should see at the bottom of the Zoom interface. So you'll be able to type your questions, and then I can ask the speakers what your questions are. Okay, so I'll just start with a brief introduction to what Reinforce is trying to do. How do I get the next slide? Oops. Okay. So Reinforce stands for Research Infrastructures for Citizen Science in Europe. So this is a EU Horizon 2020 funded project whose main goals are listed here. So we want to develop interdisciplinary scientific knowledge with the support of the citizen science. we really want this to be a two-way process, a real dialogue between the scientists and the citizen scientists. We also, although we are doing kind of fundamental research, we of course are very concerned about the environment. So many of the projects we have a connection with the environment. With the projects we have, we kind of envisage a multi-messenger approach to understanding of the cosmos. And it will also be multi-sensorial, because we not only look at things, but we will also hear things, for example, the acoustic sounds in the sea, but we also are developing a kind of an interface that allows not just visual, optical visualization of graphs and information, but also acoustic visualization. And I'll explain that a bit later. We try to have an inclusive, wide diversity, equal gender policy. And we're trying very hard to open up to citizen sciences which are impaired, senior, so we call it senior citizen science as well, and perhaps people with limited mobility. We also would like to encourage a kind of critical thinking in the world of Twitter and Facebook, where all the information is not really filtered. So one has to be quite critical and take with a pinch of salt some of the information we now are exposed to. So we want to encourage a kind of scientific approach to processing information. And we're also feel there's a very close connection between science and art. So within the Reinforce project, we will be encouraging these kind of crossovers between scientists and artists to help. We all have different ways to interpret the universe we live in. Okay, next slide. So within Reinforce, we have a number of demonstrator projects which we are setting up to allow the citizen science to get involved in high-level fundamental research. So we have a gravitational wave connection. So with this demonstrator, we will be able, the citizen science will be able to help the scientists understand the kind of noises, glitch hunting inside the gravitational wave detectors. And such understanding will help improve the sensitivity of these Nobel Prize winning telescopes for the detection of gravitational waves. Today we'll hear much more about the Deep Sea Hunter project. Another project we have is looking for new particles at the Large Hadron Collider. So we will have a demonstrator and interface to allow people to start searching for very exciting possibility of new particles at the LHC accelerator. Then our final demonstrator is an interdisciplinary project based around cosmic ray telescopes that can be used and applied to understanding geology and archaeology. So today we focus on the Deep Sea Hunter project, but throughout the year, we will also have webinars on these other projects as well. Okay, next slide. Next slide, come on. How do I get the next slide? Okay. So to work with our friends, the citizen scientists, one of our main tools will be what we call Zooniverse interface. So this is a kind of a web-based citizen science interface, which is a platform with, in fact, well, it's got 1 million volunteers have already used this platform for a wide plethora of different citizen science projects. So with the deep sea hunters, we also adopt this interface, and we're trying to make it in a way that is interesting and useful for us, and also rewarding for the citizen science. Another tool that we are adopting is Sono Uno. So this is a kind of sonification software. So instead of just, if we do have plots to help understand our data, not only can people with full visual vision see the plots, but also visually impaired people can also participate to this project. Okay. So here are a couple of examples of the Zooniverse project. Remy will give much more details of this in his talk. So on the top, you can see the current interface for the deep sea hunters. It will present various acoustic signals and allow the citizen science to classify the signals. And the example below is the search for the new particles at the LHC, where one can look for displaced vertices inside the detector, which would be a very strong sign of new physics. Okay, well, that's all I will say as an introduction to the Reinforce in general. Now we will hear much more details, firstly about KM3NIF itself and neutrinos, and then about the optical and acoustic science motivations. And I also would just like to take one opportunity to advertise an upcoming webinar, which is this one, which is so coming soon, our next webinar will be on the search for new particles at the LHC. Okay, so I'll stop there. And then the next speaker is Gwenhael. So Gwenhael will talk about, explain what KM3NIF is and what's the interest of studying neutrinos. So Gwenhael is a postdoctoral researcher at the APC lab in Paris, Astroparticle Physics and Cosmology lab. So I'll hand it over to Gwenhael. Thank you, Gwenhael. Take over. Did I stop sharing my screen? I think yeah, you're on.
I'll force you to do so.
Great.
Thanks a lot, Pascal.
Thank you.
Thanks a lot to everyone for joining us today. Thanks, Pascal, for the introduction. And as he said, I'm going to talk about neutrinos and KM3NIF. So I am an astroparticle physicist, which means that part of my job is to look at the universe and try to understand what is happening inside it, and especially the high energy phenomena that are transient sources, transient or variable sources, which means that the flux they emit is going to change over time. And I'm especially interested in gamma ray burst, for example, core collapse supernovae, flaring blazars, or compact binary mergers, which can be detected, for example, by gravitational waves, as you may have heard of. So to try to study these sources, the easiest way to do, right, is to look at them. And that's what I'm doing. But instead of doing it with light, as it has been done for centuries, I'm trying to look at them with neutrinos. And it's actually very challenging. So you have to realize that as of today, we've only seen astrophysical neutrinos coming from the sun, our sun, from the core collapse supernova of 1987, and from one flaring blazar. So we are still trying to find out which population or populations of sources emit neutrinos. So you might think, yes, okay, but why searching for neutrinos to study the universe if it is so complicated? Well, because actually neutrinos would bring complementary information about these astrophysical sources compared to what we can already learn with light. So there is a real potential there for neutrino astronomy. Another part of my job as astroparticle physicist concern particle physics and trying to understand the intrinsic nature of the neutrino. So neutrino is an elementary particle, and it belongs to the standard model of particle physics that you can see on the top left of the slide. So you see in green on the bottom line, you have electron neutrino, muon neutrino, and tau neutrino. And you might recognize other particles in this table that you have already heard about, like the electron, for example, the photon, so the light, or the Higgs boson. So although the neutrino is the second most abundant particle in the universe after the photon, after light, it still holds a lot of mysteries about itself. In the standard model that you see here, the neutrino is described as massless. Its mass is 0. But we know today that neutrinos are actually massive. We don't know the absolute value of their mass, and we also don't know how one mass compared to each other, but we do know the mass is not 0. The fact that the mass is not 0 means that neutrinos can oscillate from one flavor to another. So it means that, for example, if we consider an electron neutrino, you can see here, it might, when traveling through time and space, become a muon neutrino. And we are still working on measuring all the parameters that can explain this oscillation phenomenon. So to do so, to answer the questions about the neutrino itself in particle physics and trying to study astrophysical sources with neutrino, we are deploying a detector named CNRS that Paschal has already talked about in the bottom of the Mediterranean Sea. So you see here an artistic view, obviously, of the detector, and you can see this made of lines that are anchored on the seabed. And on each of these lines, you have 18 sensors as the one you can see here. And on each sensor, you have 31 photomultipliers, what we call PMTs. And these are actually the eyes of our detector. So these PMTs will be able to detect light. And we will see together in a moment where this light might come from. So this detector has been designed, developed, and is now deployed by an international collaboration in which many European institutes are contributing, but also institutes or universities in Australia, in South Africa, in Ecuador, or in China. And we are working on 2 different sites, as you can see here. One named Orca, which is located near Toulon in France, and another one named Arca, which is near Sicily in Italy. So let's have a look together the differences between these 2 sites. The most obvious one, in my opinion, is their size. So you see here the footprint, obviously scaled down, of Orca, and the one of Arca. So clearly Orca is going to be way smaller than Arca because the purpose of the 2 detectors are different. Orca has been thought to detect low energy neutrinos, while Arca is optimized to detect high energy neutrinos that might be produced in our universe. Another difference is the depths where they're installed due to the sites where we are deploying them. So Orca, for example, is at a depth of about 2,500 meters, while Arca will be deployed at 3,500 meters deep. So you see here the exact distance in between the lines and in between the sensor for each of the 2 detectors that in the full configuration, which is expected for 2025. But as of today, we already have 1 Arca line, so 1 Arca detection unit, so 1 point on this footprint and 6 ORCA detection units taking data. So we can already start testing our analysis, testing or channeling or simulation, etc. So how does it work? Why do we need to go to the Mediterranean Sea and install lines with sensor on them? Well, because it's very complicated to detect neutrinos. And in fact, we cannot detect a neutrino. What we can detect is the interaction of a neutrino with the medium. So in this case, water. So what's happening is that the neutrino is going to come in the neighborhood of the detector without leaving any trace. At some point, it will interact to produce, for example, an electron, which, if relativistic, so if the electron is going faster than the light in the seawater, it will force the medium to emit a Cherenkov radiation. And our sensor, as I said, remember the PMTs, the eyes of our sensors, will be able to detect this Cherenkov radiation. So practically, how does it work? We have a neutrino coming in without leaving any trace. At some point, it interacts, produces, for example, a muon, which can be seen as a heavy electron. And this muon, if relativistics, will force the medium to emit the Cherenkov radiation. And each color point you see here is one of our sensors that has seen the Cherenkov radiation. And so with this kind of event, we can actually estimate the energy of the incoming neutrino, but also its direction and its flavor. Remember the 3 flavors I talked about a few slides ago: electron neutrino, muon neutrino, and tau neutrino. So we can learn a lot actually with only installing lines with sensor on them at the bottom of the sea. So I'm very happy to be able to show you these very first neutrinos recorded with ORCA 6 detection units. So we're going to see them together. So we've added here, obviously, so these are real data, but we've added here some Cherenkov cones, so the blue cone, just to give you an idea of which sensors are seeing this blue cone light. So each time a sensor goes big, it's because he had seen some light. So you might realize that actually some sensors are getting big, but without any connection or apparent connection with the Cherenkov cone, with the blue cone. This is because there is not only a neutrino interaction that can produce light in the bottom of the sea. So there are bioluminescent species that can also produce light in the neighborhood of the detector, and this light might be detected by our sensors. What does it mean? It means that our sensors are recording light, but we don't know where this light is coming from. What we see when looking at our data is a plot that you see on the bottom right of your slides. So this is true data once again. So on the x-axis, you have the time. On the y-axis, you have the rate, which is proportional to the amount of light recorded by the sensors. So you see that this rate, this amount of light, is actually not constant over time. It fluctuates. Sometimes there is a small peak, sometimes there is a big peak. The peak might be a bit broader, a bit thinner. And so we need your help to understand these peaks, to understand and classify the different peaks we might have in our data. And this will be very useful for 2 reasons. On one hand, it will allow us to better understand our data and hence better select neutrino interactions that can be used for particle physics or for astrophysics. And on the other hand, it can also, the classification may also help us to better understand the signals sent by the bioluminescent species and maybe recognize which one are living near a detector. And Severine, Martini, as Paschal said, will tell you everything you want to know about this bioluminescent species. Because we are, our lines can be moved due to the sea current, we needed to install some hydrophones on the lines to really track the move. And Remy will tell you everything about this system in his talk. But the fact that we have hydrophones means that in addition of seeing what is happening down there, we can also listen to what is happening in the deep sea. And so we can capture signals from cetaceans as striped dolphins or sperm whale. And Hervé Glotin is going to tell you about these acoustic signals in the sea and how CN3net might actually help us to better understand them. So that's all from me, but I take this opportunity to tell you that if you're interested in CN3net, and especially by wonderful deployment pictures, for example, all the adventures that we as a collaboration are meeting when deploying such a wonderful experiment, you should join us on our social media. Thanks a lot.
Okay, thank you very much, Gwenhael. Yes, so I encourage people to join also the CN3net social media. If you want to keep up to date with the construction of the telescope, this is the place to be to find out about the progress. This year we will be doing some major upgrades to increase the size of the telescope, so you can kind of keep up to date on that. And that will of course improve our sensitivity to these bioluminescence and bioacoustic data.
So if I may add something, because it seems that at the end none of us talked about that, I also encourage you to go to the App Store if you have an iPad or an iPhone and to type CN3net. There should be a wonderful app that actually Paschal designed that will allow you with augmented reality to go into the sea and look at CN3net and play with the events by yourself to really feel what is actually happening at the bottom of the sea. So you just go to the App Store, you tap CN3net, and you should see the app.
Yeah, thank you for that advertisement, Gwenhael. So if you have any questions, don't forget to type them into the Q&A section, and then I can ask the speakers. From Claudia to, could you write the app here again? Yeah, the app is available on the Apple App Store, and you just do a search for CN3net, and you'll find it. Okay. Well, there will be a chance for more questions and answers at the end of all the talks. So let's go to the next speaker, which is Severine Martini. Severine is a researcher at the Mediterranean Institute of Oceanography in Marseille, and she's been studying bioluminescence in many nice places around the world. So I'll pass you over to Severine.
Okay, I think it works now. Hi, everybody. So my name is Severine Martini, and indeed, thank you, Pascal, for the nice introduction. So I'm a researcher at the Mediterranean Institute of Oceanography in Marseille, in France. And today, I'm going to talk about bioluminescence in the ocean. So at first, the darkness constitutes the main feature of the ocean. All the ocean is completely dark. Even the surface, if you think about that, during the night, it's even darker. Except from the lights coming from the moon, everything is completely dark in the ocean. Everything except some animals that are able to emit light, and this light emission is called bioluminescence. So bioluminescence is the light emission by living organisms. And there are some bioluminescent organisms on land, for example, fireflies, but it's very uncommon, while in the ocean, bioluminescence is very, very common. And for example, you probably heard or seen this guy, maybe in movies or cartoons. So this fish is an anglerfish, and it's able to emit bioluminescence using a small yaw on the top of its head. But actually, this one is very famous because of cinema and movies and cartoons. But there is a wide diversity of organisms that are able to emit light by themselves. For example, there are crustaceans, like this little copepod over there, which is able to emit light, and this guy is part of zooplankton. But there are also a lot of jellyfish that are able to emit light by themselves. And there are also some fishes, actually, like those guys over there. And one interesting characteristic about the anglerfish is that it doesn't emit light by itself, actually, but it requires a little help from bacteria. And those bacteria in the lure of the anglerfish are luminous. They are bioluminescent bacteria. In a recent study, actually, we found and we quantified for the first time that for animals above 1 centimeter of size, and for the ones that are pelagic, so pelagic animals are the ones that are living in the water column, then we quantified that about 3/4 of all those animals above 1 centimeter are known to be bioluminescent, to be capable of emitting light by themselves. So it's a large part of marine animals. And usually those pelagic animals are emitting in blue or green light, because this wavelength is the one which is traveling far away from the animal. So if you want to communicate with someone which is far from you, then you're going to use the blue wavelength underwater, because it's going to be more effective to communicate with someone who is very far from you. But there are some exceptions. For example, this guy is a pelagic worm called Tomopteris, and its bioluminescence is yellow, actually. So the worm is on the right, you can see it under white light, and then the bioluminescence emission is on the left, this yellow pattern over there. So this guy is pelagic, but if we are looking at organisms that are living closer to the seafloor, the animals that we call benthic, then we quantified also the number of animals, the percentage of animals that are capable to emit light. And for benthic animals, it's a little bit lower than pelagic. We quantified that about 40% of all those benthic animals are able to emit their own light, to be bioluminescent. And I wanted to show you something. So this study has been published last year. And actually, it's very interesting because this is a sponge, a marine sponge, that has been discovered at 4,000 meters depth in the Pacific Ocean. And this sponge is an unknown species, actually. So until this discovery, actually, we didn't think that sponges, marine sponges, were able to emit light. But we discovered this one, and this one is capable of emitting its own light so it's a bioluminescent sponge. And there is something even more interesting about this one. It's a carnivorous sponge. So not only it's living in a very, very deep environment, but also it's carnivorous. And then now it's also emitting light. So this is very interesting for us. So the image on the left is the sponges in situ, using a submarine engine to look at it. Then we brought it into the lab and looked at it in white light. And then we observed the bioluminescence emission, which is the green and bluish dots over there. And we used the red light to look at the sponge and the bioluminescence at the same time. So in a different study, we wanted to look at the variability of this percentage of bioluminescent organisms over depth. And we found that there is only a low variability in the water column from zero, the surface, down to 4,000 meters depth. There is always about 76% of all the organisms that are known to be bioluminescent. So the bioluminescent proportion is the one in blue here, and then the non-bioluminescent proportion is the grayish or dark gray over there. But there is something even more interesting, that this high percentage of bioluminescent organisms. So the yellow bar in this graph represents the animals that we have no idea if they are bioluminescent or not. So this is the part of undefined animals for bioluminescence capability. And what is interesting is that below 500 meters depth, this yellow bars is increasing with depth. So we have quite a good knowledge about animals above 500 meters depth, but below we have absolutely no idea about this part of like the yellow bars represented here for bioluminescence. So in summary, we still have a lot to learn from the deep ocean about bioluminescent animals. So why those animals are emitting light? Actually, there are different ecological roles, and we can classify them into 3 different categories. The first one is the defense. For example, the copepod, this small crustacean on the left, is emitting some kind of smoke screen of light. And this allows the copepod to blind a predator attacking it and then to escape. So the light is kind of the way for the copepod to escape from the predator. Then the second category is the offense category. So for example, the anglerfish, with the help of this little luminous bacteria inside the lure, then the anglerfish is going to attract prey, like this poor little fish on the picture here, and then it's going to be able to feed on them. So the bioluminescence is acting as an attraction for those little fish. Then the third category is the bioluminescence can also be used to find a partner, and for male and females in the ocean to find themselves. If we come back a little bit closer to the topic today and the bioluminescence in the Mediterranean Sea, actually we have some deep record of bioluminescence in the Mediterranean Sea at 2,500 meters depth. And we got some data thanks to a neutrino telescope about bioluminescence. So the first line in blue represents a time series of bioluminescence recorded by a neutrino telescope. So this is the photon per second over time from 2008 to 2010. And then close to this bioluminescence records, we had some oceanographic instrumentation that allowed us to get some information about salinity, temperature, and current speed. And actually, we didn't expect to get this kind of data, and we found something very unexpected based on those data sets, those time series, because in 2009 and 2010, there was a strong increase in bioluminescence intensity at 2,400 meters depth. And we were very surprised about those data, and we tried to find the reason why this bioluminescence intensity was so high. And we noticed that there was some correlations between bioluminescence and salinity and temperature, as you can see on those time series. And sometimes there was also correlations with current speed, but not all the time. So we finally explained these unexpected records by using other oceanographic data. And during cold and windy winters, the surface waters in the Gulf of Lion in the Mediterranean Sea become more dense, which means that those surface waters were sinking into the deep sea, and this can have 2 different effects. The first hypothesis is that those waters sinking from the surface down to the deep sea were bringing organisms from the surface into the deep, and some of those organisms were bioluminescent ones. And the second hypothesis is that those waters could provide a better environment for deep organisms to proliferate. And some of those deep organisms could be, for example, bacteria, bioluminescent bacteria, but not only. So what is the next step? So those data are long time series, records of a lot of organisms emitting bioluminescence. But if we are looking a little bit closer, this is some kind of flashes of bioluminescence, like individual flashes emitted by organisms. For example, dinoflagellates, copepods, shrimps, ctenophores. And what has been done in this study is that there are different patterns of light, different flashes emitted by different organisms. And what we can do is to make some kind of discriminations based on maximal intensity of bioluminescence, time of decay, the number of photons emitted over the flashes, and so on. So we can use those bioluminescent flashes to make classes and discriminating species or group of organisms, group of species. So what is the next step is that we need citizen science to help us and citizens to help us to analyze the big data set that is recorded using neutrino telescope. Remy is going to talk a little bit more about this project. If you want to learn a little bit more about bioluminescence, there is one very easy for people that are not familiar with marine sciences, for example. And there are some scientific publications that give you a little bit more information about that. Thank you.
Okay, well, interesting talk, Severine. There are some questions. Maybe I can read out. So one of the questions is about the sponge. How are you sure that it's really light coming from the sponge and it's not just some bacteria that just happened to land on the sponge and is emitting light?
Yeah, so actually the sponge story is kind of very funny because there has been some previous records about bioluminescence in sponges, but all the time that it has been published or described, then a few years later, there was like, okay, so maybe there were some contaminations from other organisms that are known to be bioluminescent, and maybe it's not the sponge by itself. So here we tried to be very careful, and we got 6 individuals, which has been very difficult because sampling at 4,000 meters depth is far from easy. So we got different individuals, and every time it was the same. Like we got this bioluminescence very easily, and then we made some biochemical assays on the sponge to be sure that it was due to bioluminescent chemicals that are related to the sponge and not to bacteria. So we try to be very careful about that. Yes. Okay. Thank you.
And then another question from Hervé was, what is the mechanism for making the light? The chemical reaction, I think. Yeah.
So usually there is some mistakes between fluorescence, bioluminescence, now biofluorescence, and all those terms are a little bit confusing, I think, for people that are not working on light. And actually, for bioluminescence, it's really a chemical reaction coming from the animals. So it means that it's a chemical reaction between luciferin and a luciferase, which is an enzyme. And then this chemical reaction, produces light at the end. But it really comes from the animal and not from light coming from an external light, for example.
I also had one question of my own, which was, for the angular fish, is its lure always switched on? Or can it choose when it's active and when it's off, on and off? Yeah, it can. Actually, it's very smart. Yeah. Those fish are very smart because they have those bacteria, and usually the bacteria don't emit flashes, in contrary to all the other animals that I've been talking about. So the bacteria that are inside the lure can be activated or not by the fish itself. So the bacteria are emitting all the time, but the fish can control if the light window. I see. Yeah. All right. Well, thank you very much, Severine. Thank you. We can come back later for more questions. So the next talk is by Hervé Glotin, who is a computer scientist at the Toulon University Computer Science and Systems Laboratory. But is now a worldwide expert on bioacoustic detection with hydrophones. So, Hervé.
Yes, I'm back. Let me share the screen. I think it should work. Do you see my screen now?
Yes, we see your screen, but not the presentation. Okay. We see all of your screen at the moment.
Yeah, because I will have some demonstration. Okay, thank you, Paschal, for the invitation, and the topic is great. And I will try to give some ideas of what we could have from your installation towards cetaceans. So we work in bioacoustics and artificial intelligence, and we analyze sounds from these animals. So these animals, as you may know, are breathing, so they get to the surface, but they also go very deep, and they dive down to 2,000, 3,000 meter depth. Here you have a visitor or a cachalot at the top left, and you can see the rorqual, which is a fin whale, and it's the second biggest whale, second biggest animal in the world. They are just living in front of Toulon. So this instrumentation is very, very well placed for cetacean studies. And at the bottom left, you can see a globicephale, which is hunting the cachalot and the fin whale. So they are hunters, they eat each other's, but also they eat what has been presented just before. They eat the life from the abyssea. And to look to their prey, because there is no more light except bioluminescence, but it's very weak, to look to their prey, they emit sounds, sonars. And to look to each other, they emit songs or voicings. So here you will see a panel with most of the species. There are 20 here, and not all of those are in front of Toulon, but there are 8 of those. And the idea to show this range of frequencies these animals emit is to start from the blue whale at the bottom, which is emitting at 10 to 500 hertz. So let me show you, or let you hear a blue whale. Okay, so this was accelerated by 3, otherwise you couldn't hear it. And as you heard, it's very low frequency for sure, and it is pulsed. So the different patterns of pulses are giving information on the group of the whale, of its family. And this is a new insight we could reinforce with this instrumentation, is to follow the population of the fin whale, which is close to the blue whale, but they are emitting the same kind of pulses, to follow their culture, because they song and the change of song according to who they meet. Okay, and then when you change from low frequency to high frequency, you get into the sonars or biosonars of the orca, of the cachalot, of the dolphins, and the patterns are then very, very short. They are just 1 millisecond long. So here you have one of these pulse emitted by a cachalot. And to compare, it's 1 millisecond long, and to compare, there is a pulse from the blue whale you heard, which is 1 second long. Okay, so 1,000 times shorter for the biosonar of the cachalot. And why should we listen to them, to this fin whale, to this dolphin, to this cachalot? They are endangered species, and they are at the top of the trophic chain. So they guarantee the equilibrium of this trophic chain, and they are maintaining the resources of the sea. If we fishes today, it's because there are whales. Otherwise, you would just fish jellies. Okay. So it's important for us, for our food, that they are still present, for the ocean. And the best way to study them is to listen to them, because they emit sounds each time they hunt, each time they communicate between each other. And what we try, and we do that for 15 years now, is to compute 3D tracks from the passive acoustics of these animals, of this instrumentation. We compute the tracks of the animals during the hunt. And one goal of this study is to avoid collision between traffic and whales. For example, here you have some damage that you see on whales or on boats. Both are damage. For whales, of course, this is lethal, and for boats, this is very damageable. So there is a win-win agreement that there shouldn't be more collisions. And here's a map at the left shows you the probability of collisions and the highest probability between different type of boats. With cachalot, for example, is in front of Toulon and Nice and Genova and south of Corsica. So again, this instrumentation is very well placed to participate to this effort of anti-collision system, and we work on that. So let me show you one important question is which sound do we receive on these hydrophones that are placed at the bottom of the sea? Here you have one column, one species. So the first column is the delphinid type A. This is the wave, the sounds they emit. So there are different individuals that have been recorded. You see the patterns are consistent. When you look to the Risso dolphins, they are different, but you agree that they are very, very similar between different individuals and different species. You can have difficulties to find who is who. And then we work with artificial intelligence, this model that is called convolutional neural net or deep learning, maybe you heard about, is very, very efficient. So we do work for speech recognition, for image recognition on that model, and we work also on new topologies to classify clicks biosonars. So we give the raw wave such that we do not destroy the information. We give the raw wave to the input of this neural network. And this neural network, step by step, layers by layers, is decomposing the signal. And then we get at the output the probability to recognize the species. And if you look at the confusion matrix, which is giving the score to recognize a signal as a correct species in the diagonal, you see we have 95% of accuracy. So it works. So why should we ask citizen science to help? Well, it works, but there is maybe not such noise that we could have in the instrumentation. There is maybe not the same boats, and the whales are maybe not at the same distance. So just to show you where we could go in better knowledge is also to track, to see the shape of the dives. And one experimentation we did, and we continue, is to use boats with little antennas and hydrophone on the keel of the boats. From these hydrophones, you get on each hydrophone the detection of the clicks. So you see the one line is one hydrophone, and you see the different arrival of the same click on the different hydrophones. And the times of the clicks, of the arrival of the clicks, is giving us information on the angle of the position of the whale. So here you have a sperm whale, a cachalot, that is clicking ta 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 on the 5 hydrophones. And if you zoom on that, you find the time delay of arrival between the hydrophones. And then you can compute angles, elevation, azimuth, and even the range. And we just did this experimentation at the Toulon in front of CCA. And here is what we got, is the track at the right here, is the track of a whale that dived 3 times, 50 minutes, in front of Toulon, just in front of kilometer cube. And to illustrate that, I will play just a few seconds a demo that shows you, and then you will hear the the sperm whale hunting. So this is real sound on another site, but it's the same situation we got in Toulon when the cachalot is diving to minus 800 meters deep. And you hear the clicks of this whale. Okay, there is a little illustration of a squid. We don't know what has been it, but in any way there was something, because it will stop in just 2 seconds. And then we can imagine that the whale did catch the prey. Okay, so if we listen carefully to the whale, we can maybe count how many preys there are. Okay, so this is a way also to know better what we have in the deep sea. Another illustration we have here is, so let me show you the general situation. On this map, you have this whale we just here at the bottom left in front of Toulon. Kilometer cube is here, okay? And I will just make you travel a little far, but in front of Antibes. And what we met at this place last January, last year, was this group of 6 whales that hunted together during 3 hours at the same place. So here is the same, and what you will see, each little ball that is moving now, that I do move, is a whale. And you see that they dive together and they keep close together and they forage together, so that maybe we think they collaborate and they emit sounds together to better look at their prey and to better guess what is the prey and to better find where it is. So here we get into a very exciting study, is that how intelligent these animals are to be able to produce sounds in collaboration to map their environment in 3D and better hunt together. So this is one of the questions that Reinforce could help to work on, because we will have details on the clicks. And just to finish, let me finish with 2 things very fast. This is another example of what is a good collaboration between artificial intelligence and bioacoustics. Here we got a record from Kilometer Cube from last spring, and this is 12 hours of recording on 3 channels, 3 hydrophones, and the colors are the probability of detection for fin whales. And there are false alarm at low frequency, but for a low level of probability. But when the level of probability is increasing, then you get the clue for the presence of the whale, and you see when in the red circle you see that a whale arrived. You see nothing before, and then the whale arrived, and then we lost it after 20 minutes. Okay, so this is a perfect illustration of what we get. And when you look at the pulses that we detected, here are the pulses we detected actually, and they are exactly as they should be from a fin whale that are 1 second long at 20 Hertz emission. Okay, so there are several pulses. There are also noise, of course, from the instrumentation. Any instrumentation is doing noise. And this is also why citizen scientists will be very helpful to precise and validate the detection we will compute. And then good luck, because here is a kind of signal you may work on. As Remy will show you, there will be a lot of noise and there will be a lot of messy things, but you will be very helpful. Okay, thank you very much. If you want more, there are some links, and I'm very happy to exchange with you. Thank you.
So thank you, Hervé, for that fascinating talk. There is a question from Otto Niemi. Can you clarify? You said that one of the aims is to reduce collision between ships and whale. Is this done by detecting whale location based on sound? I.e., is the aim to develop an anti-whale collision system for ships?
Both. We should give to boats the information of the presence of the whales. We should give to the boats the direction of the whales, the speed of the whales, the numbers of the whale, and also what they may do actually at this time, if they are hunting or just traveling. So we should give good information to boats, and boats should have good answers. So there is a lot of work there, because it's also a question how to manage the alerts we could emit. So it's very complex.
Right. I had one question of myself. Well, yes. So I think I'm correct to say that the kind of spacing between the clicks, the frequency, also gives you information about the age, the size of the whale, i.e. its age and even its sex. Is that right? You can tell if they're male or female?
Yes. Males are bigger for the cachalot. Males are bigger than the adult females. So when you get a big animal, it's a big male. When you get a medium animal, it could be a young male or an adult female. But in any case, when they are small, they are juveniles. So these are for the biosonars of several species, but it's also maybe true for the fin whales, and maybe the little variations of frequency into the pulse of the fin whales or others could give information on the individual, maybe an individual signature or information on the size, because the size of the whales is impacting the frequency of the emission. So we can get many details.
Okay, thank you.
Thank you.
I notice now we're starting to overrun a little bit on time, so I won't ask any more questions, and I invite Remy from the APC laboratory in Paris to explain to us a little bit how Zooniverse can help the Deep Sea Hunter project.
Yes, so can you see my screen? Yes, right?
Yes, that looks good.
Oh, okay, perfect. So hello everyone. It's a pleasure to show you what we are implementing on the Zooniverse platform for the Deep Sea Hunters project. And okay, so let's start. As you have seen in Gwenhael's talk and also Severine talk, we are able to detect light at the bottom of the sea thanks to KM3net photomultipliers. So we can detect light from neutrino interactions, of course, but also light coming from life forms. So with the neutrino telescope, in fact, we can study the marine biodiversity. As you have seen also in Hervé's talk, we can also detect sound, in fact, at the bottom of the sea. And the idea is that, so we are deploying line at the bottom of the sea, and because of sea currents, they are moving. And to do neutrino science, in fact, we need to precisely monitor the position of all the photomultipliers. And to do this, we have installed acoustic emitters and receivers near KM3net. So you have an example here at the bottom left of the slide of, so this is real data, and this is the monitoring of one line of KM3net as a function of time. And so you can really see this line moving and bending with time. So we have acoustic devices. We can detect the sound we emit for position measurement, but we can also detect sound from cetacean, for example. And so with a neutrino telescope, we can also study the sea mammals and cetaceans. So one of the idea of deep sea hunters is to show that with a detector developed to study something, so in our case to do neutrino science, we can do something else. And so in the case of CNRS, we can study bioluminescence and bioacoustic. So the fact is that for us, neutrino physicists, not for bioluminescence and bioacoustic physicists, of course, these bioluminescence and bioacoustic signals are noise, and we want to kind of subtract them from the data we are going to acquire. And to do this, we need to precisely understand the shapes and properties of these signals. And we need, in fact, the help of citizen scientists to better understand what is noise in CNRS. And this is why we are implementing classification activities on the Zooniverse platform. So let's go now to directly to the Zooniverse website. So I'm sorry for the shape of the windows. I have just a display problem on my computer, but it should be fine for the presentation. So this is what the front page of the demonstrator looks like. So, okay, you have a title, you have a learn more section. I'm going to show you just after. You can choose between which classification activity you want to do, so bioluminescence and bioacoustic, and you have a short presentation of the project. So let's go to the learn more section. So first, so you have two tabs. You have the research tab and the team tab. So first, the research tab is if you want to, before starting any classification, if you want to know more about neutrino science and sea science, you can go to this section. You have first a subsection, which is very short with the main fact, if you don't want to spend too much time on this. But if you want to know more, you have okay, much more details to look at. If you want to know more about us, the Deep Sea Hunters team, you have the team tab, where you have a small paragraph and a picture of all the members of of the team. Okay, so let's go to the most interesting part, which is the classification, and I will start with the bioluminescence classifications. So if this is the first time you do classification, you can go to, there is a tutorial section where we explain what to do with a lot of details. So what we are showing, basically, this is what Gwenhael has shown. So we are showing a counting rate, so in kilohertz. So it's the number of counting per second over 2 minutes. And we are asking the citizen scientists to classify what they see into 4 categories. So you have, for now, it's simple categories like 1 peak, 2 peaks, multiple peaks, and weird. And okay, I will go to the demo mode. So just for the purpose of the demonstration, I am not going to be very precise in my classification, but of course, the idea is that the citizen scientist should be very precise in their classification. So let's start with with this event. I would say, okay, it's a 1 peak classification. And then I am asked to enter some values. So first, the value of the baseline. So this is the median value of this line here. So I would say 0. Then I am asked the maximum of the peak, 0, and then the width of the peak at maximum. Okay, I would say for the purpose of the demonstration, okay, let's say 5. And I am done with this one, and I can go to another event. Okay, so this one, I would say, okay, let's say it's a multiple peak classification. Okay, how many peaks do I see? I see 3 peaks. And then I am asked to highlight these peaks by drawing rectangles. And the idea is that thanks to the properties of these rectangles, you can, okay, so in fact, there are 4 peaks, but okay, this is just a demonstration, but thanks to the properties of the rectangles, we can get the value of the baseline, the width of the peak, and also the height of the peak. Okay, and I'm done with this one, and maybe is okay. We can do this one. I would say it's 2P classification, and then I am asked to draw the baseline to identify the maximum of the peak, the width of the first peak, and to do the same for the second peak. So here we have tried to implement different kinds of activities to see which one would be the most enjoyable, I would say, for citizen scientists, because of course we want the activities to be fun to do and not overwhelming and not boring. Okay, and I'm done with this one, and I will go now for the acoustic workflow. So let's go to acoustic. Okay, so I think now I should share the sound of my computer. Okay, so now, so same as the bioluminescence workflow, you can have a look to the tutorial. Also, if you want to have some reminders. And then what we are showing are this kind of figures. So there is two parts in this figure. So at the top, you have the amplitude as a function of the time, where you can see the clicks. And here in blue, you have the frequencies as the function of time. And you can see here, there is a red line. And this is, in fact, the limit of the human audible range. All what is below this line, you can hear, but all what is above, you can't hear. So if you hear something in an audio file, this means that it's below. And last but not least, you have an audio file. Okay. So of course you can hear white noise because our hydrophone are not perfect, but you have heard also sperm whale clicks. And I notice you can see them here, they are in the audible range. So, okay. So now I can go to the classifications and okay, because I have read the tutorial, I know, okay, am I in demo mode? Yes, perfect. So this is a sperm whale click event. Then next, how many peaks do I see? Okay, I would say 5 just for the purpose of the demonstration, but obviously there are more clicks. And then the idea is to draw, locate the peaks, the clicks, sorry, by drawing some points. Okay, I'm done with this one, and let's go next. Okay, so this one, okay, I can see sperm whale clicks, but I can see also what looks like striped dolphin clicks. Let's listen to the file. Okay, so again, we can hear the white noise, the clicks from the sperm whales, but the clicks from the striped dolphin, we can't hear them because they are, in fact, above what we can hear. So let's do this classification. I would say it's a striped dolphin and sperm whale clicks event. Next. Then I am just asked how many clicks do I see in the picture, mainly because sometimes there is a lot of clicks and it's difficult to locate them. It just we are just going to ask for numbers, and then we are going to better analyze this complicated picture. So I would say, okay, let's say 8 for the sperm whale clicks, and for the striped dolphin, okay, much more. Okay. And I will say, okay, let's say 15. Okay, this is just a demonstration. Of course, I should count them more carefully. And I'm done with this one. Next. And okay, and it's the same. You have more. You have sorry, 5 categories. You have striped dolphin only, sperm whale clicks only, striped dolphin and sperm whale clicks, just background noise. And okay, maybe it looks like background noise, but it seems to be an interesting signal, and you can add some of these events to classify. Okay, so let's go to the conclusion. So this is the end of the demonstration. Let's go to my conclusion. So the demonstrator is not public yet, but if you want to know when it will be opened, you can subscribe to the reinforced newsletter. So you have the link here. And also, thanks to a discussion with the experts in bioluminescence and bioacoustics, so you have you had two presentations from Severine, Martini, and Hervé Glotin. The idea is to really understand what would be the most interesting things to do for us, but also for citizen scientists to identify what properties we should look at in the signals. And of course, thanks to this discussion, we will add new activities as we understand more and more the data we are analyzing thanks to citizen scientists. Okay, and thanks.
Thank you very much, Remy. There was a question for you. Why can't you draw a rectangle for the one peak classification like with the multiple peak?
Yes, indeed. So the idea is to test which one of the activity would be the best, but I agree that the rectangle seems to be the best one. And we are going to implement this one for all the categories, in fact, because it's fast, we can get all the information we want, like just by drawing a rectangle. So yes, we will most probably go for this solution.
Okay, thank you. Okay, I think that's all the questions I see specifically for the acoustic classification.
Thanks.
So I think we can kind of open up now to, well, we're already 16 minutes beyond the nominal time, but I think it was very interesting. So perhaps people won't be too upset about that. Okay. If people have kind of general questions, this would be the best time to pose your questions. As you see, well, I hope you've appreciated from the discussions that the deep ocean is very unexplored, and we're kind of opening a new frontier. And with CAIM3net, we will acquire a tremendous amount of data. And for example, there will be something like 2,000 when our building block is complete, there will be something like 2,000 hydrophones all listening at the same time. So this will be a tremendous data set. And we're not actually sure what we will observe and what we will see and hear. So it's kind of a new unexplored region. So we're very much looking forward to this data, and we really do need your help to understand it. And as we don't quite know what to expect, we have to learn the ways to handle this data.
Yeah, I just would like to say that we will see the invisible. The sound will give us a vision of the invisible, and at large scale, because we will listen to 10, 20, 30 kilometers away. So in a big volume. And we have other instrumentation that we deploy with sonobuoys around, and this will be merged, and it's very, very interesting. At the world level, I think it's one of the top infrastructure for sound of the sea analysis. Yes.
I see in the chat there's a question from Surienda Shaha. Why are you guys only interested in detecting intelligent life forms like macromolecular lives? What's the significance? Don't you think it would be an intelligent approach to search for the existence of baryophilic microbes, including Archaea, acting as preference for existence of life elsewhere in the universe? If we can discover why they exist in the deep sea despite the high pressure, I think it would be a helpful tool to search for extraterrestrial life. I find the talk is really very diffused in the context of astrobiology. Must admit, I'm not quite sure what a baryophilic microbe is. Severine, do you know what that is?
Those are microbes able to live under high pressure.
I see. Okay. Yes. 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 I think, didn't I read somewhere there is ideas to explore Titan, the satellites of Jupiter, with probes that would go into the methane sea and listen for the existence of life on other planets? Do you know anything about that, Hervé?
At least you know that in March we have a microphone now on March. On Mars,
Yes, that's right.
we have a mic. If you listen to, it's very nice. We have the wind on Mars, and this is the only case I know about listening.
I think there were ideas to fire hydrophones into the methane seas of Titan and listen for
Okay.
life.
I'm on.
That will be your next challenge after. There was a question on bioacoustics. How do you collect the data to know that one single corresponds to a specific animal in the first place? Do you need to do human observation at first?
Oh, a few years ago, we needed human observation at the surface, but now we have so much data sets that we can train artificial intelligence and we can use artificial intelligence to recognize species. But we still have some difficulties in some cases, and so the citizen science will be helpful, as Remy showed.
And then there's a very good question from Mohammed. How can we be part of this project? Well, that's a kind of general question for all of the Reinforce project. As you see, we're setting up, the project only started about a year ago, and we're still in the process of setting up these demonstrators. Probably near the summer, they will come online, and then the citizen science will be able to access the KM3net data and do these classifications, which we will find very useful for understanding the data. But we do want people's input so that we can improve the interface, perhaps change our methods of classification. And we're kind of open actually to any ideas. If citizen scientists can also suggest to us kind of ways to proceed, we're all ears and eyes, of course, and we will take all that information into account and trying to adapt and improve what we're trying to do. So I would say probably near the summer, our first goes at implementing the citizen science will become available, but we're certainly are willing, and we need feedback to improve everything at that point. And hopefully once COVID is no longer a problem, we can have kind of more hands-on, face-to-face type of meetings with the citizen scientists. Okay, well, I see, there's a question. Will the activities be available in several European languages? Good point. I personally hadn't thought about that, but maybe we have to do that. So maybe we can ask some of the citizen scientists to do some translations for us.
This is indeed under discussion within the consortium, and so if there is a strong interest from the community, I think of course we will try to do our best to make it available in many different languages. So please let us know, send us an email. You have all the information that Francesco put online on the chat, so contact us and show interest for multilingual activities, and we will do our best. Please do mention the language you're interested in. That will also be important. Thanks.
Yes, I think it would be useful for teenagers, especially who don't speak English well. Okay. Okay, well, I think perhaps we can wrap things up now. I don't see any more questions, and we're already half an hour over the promised time. So, so I think all the speakers can say au revoir, and I will also say goodbye. And thank you for listening. I hope it was interesting and not too boring, and we really look forward to your feedback on improving what we're trying to do. Okay, thank you.
Thank you, Pascal.
Thank you.
Bye.
Ciao.
Bye.